So on this page, we're going to take a look at a few examples in which there is an I in the denominator. And remember that I is defined to be the square root of -1. So having I in the denominator is like having the square root of -1 in the denominator, and radicals aren't allowed in the denominator. So for that reason, we can't have I in the denominator either. So as we look at number 8, our denominator is 3 minus I. And what we're going to need to do to fix this situation is to multiply the top and the bottom by what's called the complex conjugate of the denominator. So the denominator right now as it stands is 3 minus I, and we're going to need to multiply the top and the bottom by 3 plus I. This is called the complex conjugate. Now, in the numerator, I'm simply going to distribute the 2 through the expression 3 plus I, and I end up getting 6 plus 2I. In the denominator, we're multiplying a binomial times its conjugate. So this is going to require FOIL, or specifically FL, or Florida, which is what I say in my class, because when we're using the FOIL, in the case of multiplying something by its conjugate, the outer and the inner are going to always drop out. So here we're multiplying a binomial times its conjugate, the outer and the inner will drop out, and we're just left with first and last, which I nickname Florida. So the product of the first terms is 9, and the product of the last terms is -I squared. Now, from the other screen, from the other slide, we knew that I squared is -1. So in the denominator, we really have 9 minus -1, or 10. Now, every one of these terms is divisible by 2, so I can simplify a little further and say for my final answer that this is 3 plus I over 5. Okay, let's take a look at example 9. Once again, in number 9, I've got a quotient, and I have I in the denominator, which means I'm going to need to rationalize using what's called the complex conjugate. The complex conjugate in this case would be 2 plus 3I. Now, upstairs, I've got a binomial times another binomial, so I'm going to need to FOIL. First will be 10. Outer will be 15I, inner will be 2I, and the last product will be 3I squared. Now, in the denominator, I've got a situation in which I'm multiplying a binomial times its conjugate. So I'm not going to do a full FOIL, I'm just going to do a Florida, first and last. The product of the first, 2 times 2 is 4, and the product of the last would be minus 9I squared. Now we've got a couple situations where we have I squared present, and let's just review that I squared is equal to -1. So I'm going to go ahead and simplify this even further, keeping that in mind. So on the top, we've got the 10 in the front, but we really have -3 at the very end, because 3 times -1 is -3 for a net of 7. So the entire numerator is going to be 7 plus 17I, and the denominator is going to be 4 plus 9, because I squared is -1, a -9 times a -1 is plus 9, and 4 plus 9 is 13. And as I scan through 7, 17, and 13, these numbers can't be reduced at all, so this would be my final simplified answer. Let's move to number 10, which is yet another quotient, but also introduces a radical, which makes it even more scary. To get rid of the radical in the denominator here, and to get rid of the I in the denominator, once again, we're going to multiply top and bottom by this thing called the complex conjugate. In this case, that's going to be 5 minus I root 3. Now let's take a look at the numerator. We have to multiply a binomial times the other binomial. Do you think this is a FOIL situation or a Florida situation? Well, here we have a binomial and we're not multiplying by its conjugate. We're going to need to actually do the full FOIL. The first product would be 25. The outer product would be -5I root 3. The inner product would again be -5I root 3. And the last would be plus 3I squared. Now, the denominator is a situation in which we're multiplying a binomial times its conjugate. So do you think I'll need to FOIL or simply Florida, as I would say? Well, we're just going to Florida, because it's a binomial times its conjugate. The first product is 25, and the second product would be -3I squared. Let's keep in mind that I squared is -1, and now we'll simplify even further and clean this up. I'm going to do the denominator first just because it seems easier. 25 minus 3i squared is really 25 plus 3, or 28. Focusing on the numerator now, the beginning is 25 and the end is plus 3i squared, or negative 3, for a net of 22. And then the minus 5i root 3 minus 5i root 3 is minus 10i root 3. Now every one of these terms is divisible by 2, so I'm going to go ahead and simplify this all the way to the end. So we're going to get 11 minus 5i root 3 over 14. Okay, our last two examples for this lesson are on solving little mini quadratic equations which will end up having i's in the answer. So the general objective here is to isolate the squared term, then take the square root of both sides, not forgetting your plus or minus, and then what's going to happen is you're going to end up taking the square root of a negative number, so I will have to be introduced. Let's take a look at number 11. 5y squared plus 20 equals 0. Let's begin the isolation process by subtracting 20 from each side. Let's continue to isolate by dividing each side by 5. Now let's take the square root of each side. Now we know that the square root of negative 4 is now 2i, so the answer is plus or minus 2i. Okay, let's do our last question and then we'll be done. This problem is 2/3 of x squared plus 30 equals 0. Let's start the isolation process by subtracting 30 from each side. Let's continue the isolation process by multiplying both sides by 3. Let's finalize the isolation of x by dividing both sides by 2. Now I'm ready to take the square root of both sides. Forgetting to write the plus or minus is probably the biggest mistake that students make, so I'm going to circle it in red as a warning to you to never forget to write the plus or minus, because your teacher will most assuredly give you a deduction if you forget that. Now I need to break down the square root of negative 45. And I'm going to think about this as 9 times negative 1 times 5. And if I think about that expression in this way, I can simplify it down to plus or minus 3i root 5. So what I'd like you to take away from this slide is that when there is an I in the denominator, it's like having the square root of negative 1 in the denominator, and that needs to be fixed. It needs to be addressed by rationalizing with the complex conjugate in most cases. And the other element of this slide was solving little basic quadratic equations in which I becomes apparent in the answer.